Welcome everyone to lesson 3.14, the pi lesson, which is all about polar function graphs. So we're going to take a dive into polar functions. Before you freak out, yes, there are a lot of them, but we are not going into excruciating detail over them. We're not analyzing them to the extent that we did with polynomials, rationals, exponentials, logs, or our other trig functions. But we are going to explore them, their graphs, and talk a little bit about their behavior. So let's dive in. So first and foremost, how do we graph? We graph very similarly to how we graph in the past. You, one, have to take into consideration what the domain and range are. Not to the super extent, just more of like keep it in the back of your mind extent. And then you got to pick how you're incrementing your angles. Are you going to go by sixths, which is pretty pi 6, which is pretty common, pi 12ths, pi 24ths? It just depends on how clear you want your picture to be. Smaller angles make smoother curves, but they're also harder to calculate by hand. Just keep that in mind. Then you're evaluating and plotting points like you do normally. So don't freak out if you're asked to graph a polar function. You literally do it the exact same way you would do with a normal function. Something that may be helpful is to relate the graph to a rectangular version of the graph. Change the r to a y, change the theta to an x, and see what's going on. Sometimes that's helpful to see the relationships, but that's really all we got for that. Let's dive into our first relationship. It's not even a function, which boggles your mind a little bit because we're going to talk about lines. Lines in the realm of polar are not functions. Why? Because theta is your input. We're repeating inputs for lines because it's all of the points that have the same angle. So here's a line formed by pi over 3 on Desmos. And as we can see, the input pi over 3 gives us multiple outputs, so not a function. But it's similar to the equation like y equals something times x, which is how you would have to graph it in Desmos because it's not a function. Desmos isn't going to graph it. But again, you can see that it's not a function by comparing it to x equals a number. X equals a number in rectangular world gives you a vertical line, which is not a function, right? Very cool, very interesting, but we're not going to spend a whole lot of time with polar lines. The fun starts anyway with circles. There are actually 3 different ways to do circles, and it depends on how you want your circle to look. A little bit weird to say, right? If you want your circle to be centered at the pole, at the polar version of the origin, you just have to have r equals a number. So r equals a number, in this case 2, gives us a circle with a radius of 2 centered at the pole. So it doesn't matter what angle we have, we get a radius of 2. So you can compare this to y equals a number on rectangular land. You just have a horizontal line. So in polar's version of a horizontal line is, weirdly enough, a circle. Its behavior, n is equal to the radius, so whatever r is the radius of the circle. It's always centered at the pole, and remember that a negative radius produces the same graph. You just go like the opposite way of the pole. So if it was negative 2, r equals negative 2 gives you the exact same graph as r equals 2. Again, pretty cool. How do we visualize this? So on a calculator, specifically a TI-84 calculator, we can set up our calculator to graph in polar. First thing we're going to do is we're going to go to mode, check that we're in radians, and then we want to change our graph to be polar. So we're going to scroll down here to where it says function. We want to go to POL for polar. What this does is, we go to y equals, it's now r equals. Ooh, fancy, right? Next thing we want to do is go to window, and we have some things to look at here. So first thing you're going to notice is we got a lot more options. You have this theta min, theta max, and step. What this means is where are we starting, what theta are we starting with, what theta are we ending with, and it's more than likely always going to be 0 to 2 pi or 0 to pi, depending on the function we're talking about, unless you're given a scenario where the domain is restricted. That's really what we're going to play with. The step is interesting. Again, the smaller the step, the smaller the increment, the clearer your graph is going to be. 0.13. I'm not sure what this is. I might be a 24th of pi. Let's check. So if I do pi over 24, what do I get? That's what I thought. So your calculator by default would do it by 24ths of pi. You can increase that number. It will get a little bit jagged from that, less smooth, but it might take a little bit less time. The rest of it is your window as normal. If we go to the graph here, by default, you can see it's at the 10 by 10 window. We can see if we want R2, R equals 2, we're probably not going to want a 10 by 10 window. We can change this to like a negative 5 window. Negative 5 window. So let's keep everything default for now. Let's graph this one. So if I do R equals 2, what do I get? It draws the image here. But it's not a circle, Mr. Whaley. That's an oval or an ellipse, depending on how mathematical you are with it. You're right. If we hit zoom and square, that might help out a little bit. That looks more circular to me. So, again, because the calculator's a rectangular screen, if you make it equal both ways, it's not technically showing you equal proportions. So just keep that in mind. You might want to go to square if you want to see what it truly looks like. Very cool. You can also see that it went around and graphed it for us. If we go here and have this option highlighted, we can do something like this. This should trace out the steps it's taking when it's graphing. So if we hit graph, you can see it's drawing the whole thing, which is quite nice. Now I have here that the cycle is 0 to 2 pi. How do we tell what the cycle is? Well, window by default we made 0 to 2 pi. What happens if I make this pi? So second pi, just make it pi, and then hit graph. It's graphing, it's graphing, it's graphing, and stops. So since we only got half the picture, we know that we have to double it to get the full cycle. So the cycle is just how long it takes to repeat the image. If I made this 4 pi, so 4 pi, this will go around and trace the circle twice. So it's going around, so that's one whole circle, and now it's going around again to complete another whole circle. So the cycle of a polar function is the smallest period, if you will, before it repeats again and draws the exact same curve on top of itself. So that's why we just really deal with one cycle of each shape. So that is the basics of the calculator, and that is the most basic circle. Let's talk about some other circles. So what if I don't want it centered on the pole? Well, if I use r equals a cosine theta, I will get a circle that touches the pole, is tangent with the pole, and has a diameter of a. So if I now fix my calculator again, so 2 pi, and then I type in 4 cosine theta, so 4 cosine theta. So I can hit this button here to do the theta. Very, very nice. It usually pops out an x in function mode, but because we're in polar, it's going to pop out a theta. And then graph this, we can see. Very cool. But it went around twice in 2 pi. Interesting. My points here also highlight that relationship. And you can see that it started on the polar axis, moved towards the pole, away from the pole, and then followed that cycle. So, for a horizontal circle, it has a cycle of 0 to pi, not 0 to 2 pi. The absolute value of a is the diameter. If a is greater than 0, it's on the right. If a is less than 0, it's on the left. So let's graph that. So let's do insert negative, and we can see in the graph it's on the left. So, but again, it's horizontal. Not too bad. Here's what the same function looks like in rectangular, and we can see kind of what's going on here, where we have a positive value and then a negative value. So that negative radius is actually causing the bottom to occur. Kind of interesting. All right. Vertical circles. What's different? It's sine. So instead of cosine, it is sine. And we should see a vertical circle. Same idea occurs. Vertical circles have a cycle of 0 to pi. The absolute value of a is its diameter. So we used 4. Its diameter is 4. If a is greater than 0, it's going to go up. A is less than 0, it goes down. And it starts at the pole. So if I hit graph again, go off and hit graph again. Maybe not. It doesn't like me. It started at the pole and then works its way back. So cosine started on the axis and moved itself. Sine starts at the pole and moves itself. So that's something interesting, a little bit different between the two. But again, not that bad. So 3 circles, r equals a number, r equals a cosine for a horizontal circle, and r equals a sine for a vertical circle. Not that bad. Now we get to a more complex polar function, arguably one of the prettiest, roses. So roses have 2 different polar functions. So circles have 3, roses have 2, but there are 4 different patterns of behavior based off of the 2. So what's different is instead of a cosine theta or a sine theta, we're now giving the theta a coefficient. So that is going to produce rose petals or flowers, if you will. It's called rose curves, but whatever you want to call it. The major difference occurs when n is odd or even. So let's look at some odd ones first. So if I do 4 cosine 3 theta. Oh, these are supposed to be thetas. Oops. We get, look how quick it is. We get these nice petals or fan blades or whatever you want to call them. Notice how it went around twice for 0 to pi. Interesting. So its cycle seems to be 0 to pi. What happens when I change it to sine? Oh, first, I missed it. Let's do this again. It starts on the polar axis here and then works its way around, right? It's got to stop. For sine, instead of starting at the polar axis, it's going to start at the pole. So a common misconception is that sine is always vertical and cosine is always horizontal. Cosine is always horizontal with the pole axis, but sine is not always vertical. As we can see, it didn't always go up here. Now, if I do negative sine, it will flip, yes. But just keep that in mind. Just because it starts at 90 degrees or pi over 2 up doesn't mean that it's going to be sine. So if we look here, we have 3 petals, and the petal length is 4. So looking at the behavior there, kind of interesting. What happens if I change it from 4 to 3 and the 5 to a 3 to a 5? We get shorter petals. It still goes around twice per the period we set up. The petals are shorter and we have more of them. So there's 5 petals, 3 petal lengths. What does this mean? For odd behavior specifically, n is the number of petals. A is the max length of the petals. Cosine, remember it starts and is aligned with the polar axis. Sine, it's not aligned with the polar axis. It starts at the pole though. And its cycle is 1 pi, 0 to 1 pi. Interesting. What happens if n is even? So the first one we have is 4 cosine 2 theta. So let's try that. So 4 cosine 2 theta. 1, 2, 3, 4. And it only went around once. Interesting. Sine, what happens there? What happens if we change it to sine? Start at the pole. Interesting. Very cool. So, same kind of shape, just rotated about pi over 4. Very cool. Kind of looks like a 4-leaf clover, right? What happens if we do longer petals, so 5, and we change the 2 to a 4. Well, it's going to go super fast now. Interesting. So we don't have 4 petals, we have 8, and we didn't have 2 petals before, we had 4. Very, very cool. So what does that behavior tell us for even roses? So for even roses, we have 2n petals. So we double the even number, and that gives us the number of petals. A is still the max length of the petals. Cosine still starts on the polar axis. Sine still starts the pole. But the cycle is 0 to 2 pi for one whole cycle. Very, very interesting. And I think that's really, really cool. Again, they're very pretty, and you can play with them to see all of the symmetries that they have. Just very, very cool functions. So let's determine the type of polar function and its behavior. We're going to try to do this without a calculator, and we'll check ourselves, right? So first thing I notice is that we have something inside. So that tells me it's not a circle. It's going to be a rose. So this is a rose. And it's an odd rose. So it's a rose with 7 petals with a petal length of 2. And it starts on the pole. So there we go. Its cycle. Odd roses have a cycle of 0 to pi. So its cycle is, oh, it did not like that. 0 to pi. What about this one here? We don't have anything in with the theta, so this is a circle. It is a vertical circle. It has a diameter. Oh, did not like that. Let's erase that. All right. A diameter of 9. It is vertical. And its cycle is also 0 to pi. Here we have something on the inside. So this is a rose. It's even, so double. It has 12 petals. The petal length is 8, and its cycle for even roses is 0 to 2 pi. How do you know some of this stuff? Some of this stuff you're going to have to memorize, but you can see relationships between them, and I encourage you to find them. Let's double check our answers, because it's no fun just to assume that we're right. If we do 2 cosine 7 theta. So it definitely went over itself twice. So the cycle is right. The length and the number of petals is a little hard to see, right? So let's go to format. So we're going to do second format. Let's turn the axes off. And if we count them now, 1, 2, 3, 4, 5, 6, 7. So that's good. And the length should be right if we turn the axes back on. Ooh, we can do this. Ooh, what is that? Nothing. All right, but it's 1 too long. So, as we expected, right? If we change this to 9 sine theta, we get a vertical circle, and it's repeating again, so we got the cycle right. And we know the diameter is right. I'm not going to mess with the calculator for that, but we could if we wanted to. Last but not least is this one here. So we have 8 sine 6 theta. Now, look how jagged these are, right? Look how jagged these are. They don't look very pretty or smooth. You can increase the step. You can decrease the step. You can cut the pi of 24ths into pi 48ths or something like that, and that should help. Let's count the petals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're good there. So there we have it, right? Now, can we, given a graph, write the equation for each of these? So we have a horizontal circle here, and its radius is 2. So we know that this is going to be r equals 2 cosine, and since it's a circle, it's just theta. Not that bad. We have a rose here. We have a rose, and it doesn't start on the polar axis, so it is sine. So we have r equals something sine. We have a length of 1, 2, 3, 4, so this is 4 sine, and it's got 4 petals, so you divide that by 2 theta. Very good. Now we have a circle again. It is a vertical circle, so it's sine, but it's down, so it's negative. It's got a diameter of 1, 2, 3, 4, 5. So this is r is equal to 5, negative 5 sine theta. Not that bad, right? Super not that bad. Now it wants us to sketch a graph of each polar function. So we're going to graph them on the calculator and then find the endpoints using the restricted domain and then highlight each restricted domain. So I'm going to switch back to, let's do let's do green here. Green probably looks less jarring on the eyes. R equals 3, we know that's going to be a circle with a radius of 3. So we could graph that now if we wanted, or we can just go to the calculator and change this to clear 3. And again, we want it to show us the curve, so we're going to go here, change this until it gets to the little circle with the line trailing behind. Let's graph this, and we can see that we are right. It is a circle centered at the pole with a radius of 3, so bear with me now. Oh God. So, not quite super circular, but you get the idea, right? Now what's the endpoints of pi over 6 to pi? How can we figure that out? Well, for a circle like this, it's pretty easy to do, but we can use the calculator to help us. If we go to Window, and we change the min and max to pi over 6 and pi, we'll see something happen. So, pi over 6, and then pi, in a graph, it starts there and ends there. So we can see very, very clearly that it starts here and ends here. So we have this part of the circle. Not that bad, right? Let's change back what we changed to pi. And let's look at this one here. So we know that this is going to be a rose with 3 petals and a length of 4 for each petal. But let's graph it to see exactly what it looks like so we can trace it quite nicely. And it's quite quick, right? So it's got a length of 4. So if we go back to the pen, it's got a length of 4. Kind of goes in. Then it goes down here. Oop. Let's erase that. Then it goes down here. So length of 4. And then it goes up here with length of 4. And then it goes back over here. So super awesome job. We did a great job. It looks beautiful, right? I did awesome. I don't think it's aligned with pi over 4. Just to let you know, I don't believe that's what's going on. I think it's probably the pi over 3s, which I messed up on, but it's a sketch, right? Let's look at the endpoints. So if we go to Window and change our endpoints, we want pi over 6, and then we want pi over 3. What does that give us? It gives us the start of half of a petal. So it gives us from here to here, essentially. So I was right. It would have been pi over 3. It should have been with this 4 pi over 3. But I digress. We kind of see the comparison here, right? Now we have 5 sine theta. That's a circle, vertical circle, right? So we go here. We know that it's going to be 5 sine theta. We know it's going to be a vertical circle with a diameter of 5. Let's change our steps, or our min and max, to be 0 to 2 pi again. Graph this. We can see exactly what we predicted. So as far as the pen goes, we have a point here, and we are doing our best to make that as circular as possible. Oof. Now I want pi over 2 to pi. I have a good idea in my mind's eye what that's going to do, but we can always check that with a calculator. So pi over 2 and pi, and that gives us top, so it gives us the left side of the circle. So, not that bad, right? Those are circles and roses that we really did some exercises with. There are more. We have more polar functions. Hurrah! Who said this wasn't a long one? Let's start with arguably, in my mind, one of the coolest, but also one of the simplest polar functions, which is called an Archimedean spiral, or just Archimedes spiral, or just a spiral. How do you get a spiral? You get a spiral by using an equation in the form, a function in the form r equals n theta, where n is a real number. So if I go here and I just do let's delete. If I just make this theta, I get, we got to change our steps back. Starting at 0 and ending at 2 pi, we can see the makings of a spiral. Now, probably not going to be, there we are. So we have the makings of a spiral there. Very interesting, very cool. The only reason it stopped is because it stops at 2 pi. It can and will keep going if we let it. So this doesn't have a cycle. So it doesn't have a lot of the behavior that a lot of the other ones do. But again, very, very cool. There are some very cool aspects about this function. And that's an Archimedean spiral. The next ones, I apologize to anyone who speaks French natively or has learned French in a French class. But we're going to talk about limaçon. Okay. Next up, we have limaçons. I'm going to call them snail functions. I'm sorry. My French is awful. I learned Spanish in high school, so I apologize now. But there are 4 major types of snails, of limaçons, all of which originate from one of 2 forms, which is a plus b, or a plus or minus b cosine, or a plus or minus b sine. So, limaçons, there are 4 major types. They all have some resemblance to snails, which is why they are called snails in French. Fun. So the first one is called the cardioid. I'm going to call it a cardioid, which is a heart-shaped limaçon. And this occurs when the A is equal to the B, or the ratio of A to B is 1. Again, it could be -1 as well. Like the plus or minus doesn't matter. We're using the absolute value of these numbers when we talk about these relationships. So if I have 3 plus 3 cosine, I can see I get a beautiful heart shape here. And this is what it looks like rectangularly. And we can see that we start the furthest away, we move to the middle, and then we touch the pole, and then we move away until we get to the furthest away that we're going to be. So that's why these shapes occur, is because rectangularly it just touches the x-axis. So that's really, really cool. Again, this occurs when A is equal to B, or the ratio of A to B is 1, if you want to think about it that way. What if A is larger than B, but the ratio is somewhere between 1 and 2? This essentially means that instead of touching the x-axis, it always stays above. We get what's called a dimpled cardioid, or a dimpled limaçon, which kind of looks like a heart, but it doesn't go all the way down to the pole. So rectangularly, again, it's because we're not touching the axis here. what happens if that ratio is greater than or equal to 2? So if A is greater than B by 2 or higher, by a factor of 2 or higher, we get what's called a convex limison. And the higher that ratio is, the more circular that looks. So it almost looks like a circle that's not tangent to nor centered at the pole. And this occurs because the distance between that's oscillating between the middle is so much farther away than the x-axis is. So it's not getting close enough to the x-axis to show any of that behavior, that cardioid-like behavior. So the last but not least is what happens when A is less than B, or the ratio of A to B is less than 1. You get what's called an interlooped limison, or you get your actual snail shapes. So you have these beautiful curves within curves, and this happens rectangularly because we are dipping below the axis. We are going through the axis at some point. So those are your 4 different types. You have, again, repeating again, you have your cardioid, your dimpled, your convex, and your inner loop, all limisons. All of them, every single one of them, has a cycle of 0 to 2 pi. Cosines are always aligned to the left and to the right. Sines are always aligned to up or down. And we can see an example, if you would like. Oh, it froze on me. Oh, no. Refresh. All right. So I got to change this back to be polar. Zoom square. Sure. That looks fine to me. Let's do something weird. Let's come up with one on our own. Let's do an inner loop one. So we want the coefficient of the sine or cosine to be larger than the number we're adding. So let's do let's go big or go home. Let's do 2 minus 6 sine theta. And we can see we have that interloop limison. And it is going down because we used a minus with sine. So that's the behavior of limisons. Again, if I'm saying this wrong, I wholeheartedly apologize. I am not trying to insult anyone here. I'm just trying to do my best to actually say it so it resonates. So we have the graph of a polar function. We can see it is a dimpled limison. So we need to come up with the equation for it. All of these are dimpled limisons because the A is larger than the B. So what's happening here? Well, we're going up. So if we're going up, it is sine, and it's sine plus. So we have this one here that we're going to pick. We can also see that it's 6 away here and 2 away here. Adding them together gives us 6. Subtracting them gives us 2. There we go. If the domain is restricted, what is happening? Interesting. Is the function positive or negative? Is the function increasing or decreasing? That's hard to tell, right? So what we need to do is we kind of need to graph it in our minds. What is happening here? Well, this is above, and it's sine, right? So its middle is 4, it's sine, so it's going up, middle, down, middle. And for pi over 2 to pi, we are here to here. So what is happening? It is positive. We can also see clearly from the left to the right that the function does decrease. Graph the function in rectangular form, just switching out the r's and the thetas for y's and x's, and that should give you a clear idea of what's going on. Let's try this one. We have an interlooped limison, which I think are the most snail-looking ones. What is the equation for this one? So it is horizontal, so it is automatically cosine, and it's left, so it's going to be subtraction. Now it's asking about its behavior. So if I were to graph these, we have a midline of 2, So we have a midline of 2, and its cosine, and we're subtracting. So since we're subtracting, we're starting under, so it would be under, a down, middle, up, middle, down. And again, we're looking from here to here. It is positive, and it is increasing. So again, pretty easy to tell once we switch to rectangular. Last ones, and they're kind of a bonus. I have no idea if these are going to be on the AP exams or not, but they are super cool functions regardless, is called lemniscate. Interesting. So last but not least, we have lemniscates, which are infinity figure 8 style functions. And there are 2 different forms. There is one with cosine and one with sine. And they look very similar. They look like roses. The major difference is that the R and the A are squared. And they specifically have a 2 here. So that's great. That's all beautiful and all that. But if you're using Desmos or you're using a calculator like a TI-84 like we have here, you have to square root both sides, which gives us R is equal to A square root of cosine 2 theta. So if we want a horizontal aligned, if we want one that starts on the polar axis, we have to use cosine. Not starting on the polar axis, we use sine. So again, you have to be careful. It's not vertical and horizontal. It's on the polar axis and not on the polar axis. Their cycles are 0 to 2 pi. A is the max distance. And again, what I said before, you can think of these as roses with 2 petals, which you can't do with normal rose curves. So that's where you get that infinity from. If we want to graph one, let's do... it froze again. So if we want to graph one, we have to do, let's do like 6 square root of cosine 2 theta. And then we want to turn on our trace tool. So you can see. Oof, it did not like that. All right, so take it with a grain of salt. I guess the TI-84s have trouble with it. Desmos, you will get these beautiful curves by just taking the square root. I'm guessing there's some weirdness that happens there. Do your best with it. Again, these are kind of weird. I just wanted to show them off because they are a different type of polar function, and a lot of textbooks and stuff talk about them, so I wanted to make sure to bring them up. If you have any questions about any of this, please ask. In my class, I'm planning on letting you kind of explore these functions a little bit more, play with them a little bit more. But that is essentially it. We're not going super detailed, super in-depth. We're not analyzing these to the extent of what we did before. Just kind of introducing all of these so we have a baseline understanding of all of these different polar functions. So that is it, and I'll see you in the next lesson.